Right now, as we speak, 3I Atlas, an enormous glowing object the size of Manhattan, is speeding toward Earth on what appears to be a planned, coordinated trajectory. It's going so fast that you could fly from New York to Los Angeles in just 1 minute.
A silent traveler from another star has slipped into our solar system, sparking a rush of telescopes, papers, and debate. Astronomers call it 3I Atlas, the third confirmed interstellar visitor, and they've been racing to separate hard data from hype. Here's a clear, up-to-date overview of what we actually know, what's still uncertain, and why this object is so unusual. Let's cut through the noise. Discovery and early buzz. 3I Atlas burst onto the scene. In early July 2025, when NASA's Atlas survey in Chile identified it as an interstellar object. It follows in the footsteps of Oumuamua 2017 and Borisov 2019, but early estimates suggested it was traveling even faster, about 58 kilometers per second, and could be ancient, perhaps 3 to 11 billion years old. The discovery triggered a global observing campaign and a rapid surge of research. Only a handful of papers existed in July. By September, dozens more had appeared, refining size, activity, and behavior. Archival and wide-field data quickly extended the observational timeline. NASA's TESS mission, designed to find exoplanets, inadvertently imaged 3I Atlas from May 7 to June 2. These deep stacks let astronomers cross-check brightness and motion, and they revealed something unexpected. As the object closed in on the Sun and TESS by 0.9 AU, it brightened far more than simple distance effects predicted. Its flux rose by a factor of 5, not 1.5, pushing the visual magnitude to 19.3. Evidence that 3I Atlas was already highly active at large distances. Comparisons to earlier interstellar visitors help frame expectations. Oumuamua's light curve baffled researchers and hinted at a non-typical shape and surface. Borisov behaved more like a classical comet, but was notably carbon chain depleted. 3I Atlas appears to blend traits. A smooth, hard-to-modulate light, curve that obscures clear rotation signals, combined with increasing outgassing and dust as it approaches the Sun. Ground-based photometry favors a rotation period near 16 hours, though earlier space-based data were too noisy to lock this in. Space and ground observations. The Hubble Space Telescope used target of opportunity time to image 3I Atlas on July 21 at a distance of 446 million kilometers. Stars trailed in the background as Hubble tracked the comet, and the images showed a teardrop coma with dust streaming away. Crucially, Hubble constrained the nucleus to a few hundred meters, up to about 5.6 kilometers across. Much smaller than early, coma-contaminated estimates that had placed it nearer to 10 kilometers. This down revision dramatically changes mass and rarity arguments. On August 6, the James Webb Space Telescope observed the coma with its near-infrared spectrograph. The spectrum and morphology suggested complex outgassing. Carbon monoxide and carbon dioxide were driving activity more than water. At that stage, a situation expected to evolve as solar heating increases. Webb and subsequent analyses also noted surprising forward-scattered dust. Some material appears to stream toward the Sun's direction in the sky, likely due to grain fragmentation and gas pressure pushing particles away from the nucleus and enhancing reflected light. Back on Earth, Gemini South imaged the comet in late August, with multicolored data that clearly showed a lengthening tail, significantly longer than in Gemini North's July frames, implying rapidly increasing activity on the approach to perihelion. Spectroscopy during the August run and follow-ups detected CN, a daughter product of HCN, which usually appears once comets cross inside 3 AU. Production rates neared just over 3 AU were modest by solar system standards, on the order of 8 times 10 to the 23rd CN molecules per second. But diagnostic ratios placed 3I Atlas among the most carbon chain depleted comets measured so far, echoing Borisov's chemistry. TESS and Hubble constraints together point to another striking fact. 3I Atlas was likely active at 6 AU, well beyond the water ice sublimation zone. That hints at hypervolatile drivers, CO, CO2, maybe N2, or even H2 trapped in ices. Initiating activity earlier than typical for solar system comets. Chemistry and polarization. Findings. Chemically, the comet's carbon chain depletion means the coma and tail lack the longer carbon molecules, C2 and C3 relative to CN that many comets show. One estimate placed C2/CN at less than 0.09, a very low ratio. Because such taxonomic labels often reflect formation conditions, 3IATLUS may have condensed in a cold, carbon-poor region of its natal system. Still, the interstellar sample is tiny 2 comets and 1 asteroid-like object, so patterns remain tentative. A major surprise arrived from polarimetry. Measurements across Chile, the Canary Islands, and Bulgaria revealed an unusually deep, narrow negative polarization branch for 3 Sanayatel, US light scattered with polarization. Parallel to the Sun comet observer plane rather than the more common perpendicular alignment. Borisov showed predominantly positive polarization. Most solar system comets cluster along familiar curves. 3I Atlas's outlier signature suggests its dust grains, their sizes, porosities, or surface structures differ in ways we have not seen before. Some trans-Neptunian objects and centaurs show weakly comparable trends, but 3I Atlas appears more extreme, hinting at a distinct class of small bodies, or at least a markedly different dust environment. As activity ramps up, chemistries and polarimetric signals can evolve. If 3IATLUS fragments, a real possibility for fragile, dirty snowball, comets' fresh ices could spike water and other volatiles, brighten the coma, and alter the dust population. Observers are watching for changes in C2 production, CN strength, and the polarization phase curve as solar heating intensifies. Debate and what's next. Public interest spiked when high-profile commentary proposed exotic explanations, including alien technology. Early arguments leaned on an overlarge nucleus, 10 kilometers, that would make such an interstellar arrival improbably rare. But those estimates predated coma-aware analyses. Hubble's July imaging capped the nucleus at 5.6 kilometers. With updated size and natural dynamics that reproduce the current trajectory, mainstream interpretations do not need engineered maneuvers. 2 rebuttal papers methodically addressed claims about non-gravitational acceleration and planetary flyby coincidences, showing that ordinary physics fits the data far better. Speculation is not off-limits in science, but new claims must track new measurements. Amateur observers have contributed too. During the September 7th, 8 lunar eclipse, astrophotographers in Namibia captured 3I Atlas with a vivid green tint. In many comets, that hue comes from C2 fluorescing near 518 to 520 nanometers under solar UV, but given 3IATLUS's carbon chain depletion, any strong green glow is intriguing. It may signal rising C2 as heating increases, or it may be an imaging artifact that professional spectra will clarify. Either way, It's a beautiful reminder that discovery is a shared enterprise. Looking ahead, 3I Atlas reaches perihelion around October 30, at roughly 1.4 AU. It will be too close to the Sun for safe viewing right around that date, then should re-emerge by early December for renewed observation campaigns. Expect continued monitoring by Hubble, JWST, Gemini, and likely contributions from SOHO and other heliophysics assets. Key questions remain. How will activity change at and after perihelion? Will the nucleus shed fragments? Can refined astrometry and chemistry constrain its origin, perhaps a cold outer reservoir around another star? What we've learned so far is substantial. The nucleus is smaller than first thought. The comet was active far from the Sun. Its brightness surged beyond simple geometry. Its dust and gas behavior are complex. Its chemistry is carbon chain poor. And its polarization is unlike any comet or asteroid yet studied. Together, those facts mark 3I Atlas as both a cousin to known comets and an ambassador of unfamiliar conditions, carrying clues about planet formation beyond our system. Amid all this, a practical note: careful, patient analysis, stacking images, modeling light curves, parsing spectra, comparing polarimetry beats hot takes every time. The story of 3I Atlas is still being written, and the best answers will come from the slow accumulation of evidence across many instruments and teams. Whether it quietly rounds the Sun or surprises us with a breakup and flare-ups, it will leave behind a trail of data that sharpens our picture of how small bodies form and evolve around other stars. Thanks for watching. Don't forget to subscribe to Epic Dive for more amazing documentaries.